So our final speaker is Malte Schütze. Malte will be speaking on the verification of fair control system using the deterministic network calculus. Malte is a computer science student at the University of Kaiserslautern, and this talk is a summary of his bachelor's thesis.
Yes, thank you. As I've been introduced, I can skip over my usual introduction. So let's get to some background. The fair control system has an alarm-based design, which means that the time where messages are sent out is disjunct from the time where the command is actually executed. However, because once a message is sent out, it can't be cancelled, but we would still like the control system to be flexible and respond to input changes. The actual message is only sent shortly before the deadline. So at the fair control system, this is about 500 microseconds. But if we send this message so shortly before the deadline, we would like to give guarantees that no matter what inputs arrive in the system, we never exceed a latency of these 500 microseconds. Now, that's usually not a problem if the network capacity exceeds the data generated by a large amount, but the fair is also designed to carry multiple experiments in parallel, and so we would like the network to be actually used at capacity. And in fact, we already know that it will be used at capacity, so we need a verification step which allows us to give these guarantees. So one framework for this kind of verification task is deterministic network calculus. The idea is to model the network as a set of curves, which can then be analyzed to derive end-to-end delay and backlog bounds. And there are tools available which support this analysis for complex networks, for example, disco DNC. So the core concepts of deterministic network calculus are that we have two kinds of curves. On the one hand, we have arrival curves, which represent an upper bound on the traffic entering the system in any given interval. So, for example, if you consider a system which sends data at a rate of about 500 megabit per second until some buffer runs full, at which point we switch to a lower rate of 100 megabit per second, that system would have the arrival curve shown here in the upper graph. On the other hand, we have service curves, which represent the forwarding capabilities of the system. So what this means is that in any period in which the system is backlogged, the service curve is a lower bound on the traffic emitted by the system. So, for example, a network link with a latency of 2 milliseconds and a rate of a gigabit per second would have the service curve shown here on the lower graph. And this is combined with operators which allow us to chain methods and which allow us to chain curves and which allow us to construct complex networks from fairly simple building blocks. So, however, tools are usually restricted in what kind of input curves they accept. In particular, the disco DNC is restricted to arrival curves, which are both concave and piecewise linear. And the question now remains is, how do we transform these message sequences, which are basically mini-programs and non-deterministic, how do you transform this into an arrival curve, which can be processed by the disco DNC? So, as I mentioned earlier, the arrival curve is an upper bound on the traffic entering the system in any given interval. And this means that we can actually just consider all message sequences of a length I and pick the maximum traffic generated by any of these sequences for our value of the arrival curve at I. We can see that the arrival curve is subadditive, which is good because one of the core results of network calculus is that any non-subadditive arrival curve could be self-improved by subadditive closure. But in particular, in our case, it also means that we can find an upper approximation of the arrival curve by evaluating it up to some fixed threshold and then repeating it periodically. So what we have there is a pseudo-periodic function with a period of k and an increment of alpha k. And again, this is good because, as I said, we want a concave function. And the concave hull of a pseudo-periodic function is particularly easy to calculate because we know our concave hull will consist out of linear segments We know that each segment will have a lower slope than the preceding segment because that's the concavity constraint we're having. And the pseudo-periodic function gives us the slope of the last segment, which is alpha of k over k. So at this point, we can recursively construct our curve backwards by trying to pick the next segment, checking if it still adheres to our concavity constraints. And if it does, we can try to construct the rest of the concave hull. If it doesn't, we backtrack, try to pick another candidate for our segment, and we repeat this until we have found, finally, a concave hull. So we now have an approach that works in theory. There's still one problem we need to solve, which is the time it takes to calculate this whole thing. Because fair specifications are accurate to a nanosecond. So just brute forcing the calculation would actually cost us a lot of time and memory. And additionally, since these message sequence diagrams are non-deterministic, we also have an exponential blow-up whenever we leave one of these blocks of the specification. However, there are certain countermeasures we can take. For one, we can see that there's usually only about 10 to 100 messages sent per second. So if you use sparse data structures, we can actually drastically reduce the amount of memory our algorithm consumes. That in turn enables us then to cache all the values we require. And that alleviates exponential blow-up. Finally, it's actually possible that we calculate the point at which our arrival curve changes the next time. And so our calculation can skip all the time steps in between, which are not of interest to us. If we put this all together, we have a theoretical runtime of the algorithm, which is squared in the number of blocks of the specification, and also squared in the number of steps of the final curve. That's at least in the theory. So let's take a look at what happens in practice. So we evaluate this algorithm with respect to the threshold k, which is the threshold we picked for our subadditive approximation earlier. And we evaluate this on a fictional but representative specification for which we actually know the optimal solution. So we first look at the accuracy. And as an indicator, we use the slope of the final segment of our hull, which we can do because we know that the hull itself, the error introduced by it, is A, fairly small, and B, independent of the threshold we use. And we also know that up to the threshold, our approximation just copies the values of the actual arrival curve. So the only inaccuracy which is of interest here to us is the inaccuracy introduced by the periodic repetition of the arrival curve. And that's exactly what is represented by the slope of the final segment. So shown in red here is the slope of the optimal solution, which is about 2 times 10 to the minus 6. And in blue is our approximation. And we can see that it converges fairly quickly to our optimal solution. And it seems to reach the optimal solution at about 10 to the 7 to 10 to the 8th. But we'll look at some specific values later. First, let's also look at the time it actually takes to calculate our algorithm. So this whole measurements were taken on my laptop, so Intel Core i7. So they are also not meant to be authoritative, but they give a nice intuition about what the scaling of the algorithm actually looks like. In fact, we can see that there's a small but fixed overhead at low threshold values in the low millisecond range. And for larger threshold, we begin to scale linearly with the threshold. So if we look at some specific values, we can see that between 10 to the 8 and 10 to the 9, our error drops below 1 percentage point. And we're still fairly fast. So we can calculate it at this point in about 50 milliseconds. And we can drop the error arbitrarily small by increasing our threshold. So at this point, scaling starts to catch up with us, and now at 10 to the 10, it already takes us a third of a second to finish the calculation. But that's usually not a large problem because generally this verification step is part of a longer verification chain and reconfiguration process, which takes more than a couple of days. So in summary, we now have an algorithm which is reasonably memory efficient, which is actually fast enough for interactive use. As I said, it's not strictly necessary to have it interactive, but it's nice to have this interactivity for rapid prototyping to get the feeling for what threshold one actually needs for the verification later. And so in general, we have a really good speed to accuracy trade-off. Now, the next steps would be to use the model of the network we have in combination with the arrival curve we derive from these traffic specifications to actually derive delay bounds and guarantee that any execution path we can take actually remains within these delay bounds. But that's out of scope for this work, and I'm actually also out of time. So that's it. Thank you.
There's time for questions.
Hi, I'm not familiar with this verification technique, but I would like to ask you if you consider before using this network, how do you call it, sorry, network calculus, you consider any other verification technique? And the second question is, how long does it take to create those models or those equations that you use? Thank you.
So your question is how long it takes to derive the rest of the model of the network, right?
To produce the model.
Okay. It really depends on how accurately you want to model the network. At least at the fair, the whole network structure is actually a graph, so our bottleneck is right at the top where the master node sits. So a really naive model of the network would just consider the bandwidth and the latency of that link, and that would give us a pretty good approximation. But you can arbitrarily scale that up by considering the whole network and side traffic introduced. And,
These models can be somehow automatized. You can actually produce these models because actually you are checking that you don't check the implementation, you check the specification of the system, do you?
I'm sorry, I don't.
Do you actually, you are verifying the specification, right, of the system, never the implementation?
Well, the specification shows us what communication can potentially happen. So what we are actually verifying is the communication, yes.
So your models are based on the specification. That's what I mean, right?
The arrival curve model is based on the specification because that's what actually changes with the specification. The rest of the network model would depend on your network topology.
All right. So my first question was, any other alternative to this?
Probably. I actually entered the whole process after network calculus was already chosen. So I can't exactly comment on what other verification purposes were considered. Maybe Matthias could give some more details.
One more, I think.
Hi. I created the model of the fair control system as part of my PhD thesis, and it's the reason deterministic network calculus was chosen is that we compared it to several approaches in queuing theory, and the problem is basically that queuing theory is very generic, and the deterministic network calculus focuses on worst case analysis. And this is exactly what we wanted, because we're not that interested in throughput. We're not that interested in fully optimizing the system as long as we cannot guarantee that it all arrives in time, because it's hard real time, so a late message is as good as a lost message. This is why we chose this, because it's tailor-made for that purpose.
Thank you.
Okay, this sounds like a good discussion for the coffee break. So this officially ends the thing. Let's thank our speaker once more.
Thank you.